Welcome to today's paper reading. Today's paper is titled, MAmmoTH2, Scaling Instructions from the Web. This paper was published on the AR14 preprint by Xiang and colleagues from Carnegie Mellon University and University of Waterloo. Instruction tuning significantly enhances the reasoning capabilities of large language models, LLMs. The quality and scalability of the data used are critical factors. Most instruction tuning data currently comes from human crowdsourcing or GPT-4 distillation. In this work, a new paradigm is proposed to efficiently harvest 10 million naturally existing instruction data from the pre-training web corpus. This involves recalling relevant documents, extracting instruction response pairs, and refining these pairs using open-source LLMs. Fine-tuning base LLMs on this dataset results in the creation of MAmmoTH2 models, which show a significant boost in performance on reasoning benchmarks. Notably, the performance of MAmmoTH2-7b, Mistral, increases from 11% to 36.7% on math and from 36% to 68.4% on GSM-8K without any in-domain data training. Further training on public instruction tuning datasets yields MAmmoTH2+, achieving state-of-the-art performance on several reasoning and chatbot benchmarks. Figure 1 provides an overview of the performance results for MAmmoTH2+. The MAmmoTH2-8x7b+ variant demonstrates superior performance on reasoning benchmarks compared to Mistral Instruct, achieving results comparable to Qwen 1.5-110b but with significantly fewer active parameters, 13b. Additionally, it outperforms Mistral Instruct by approximately 10 points on general code and chatbot benchmarks, highlighting its efficiency and effectiveness in these areas. The paper addresses the limitation of large language models, LLMs, in performing complex reasoning tasks, particularly in domains like mathematics, science, and engineering. To enhance these models' reasoning abilities, the authors propose a novel method called WBINSDRUCT. This method involves a three-step pipeline: recall, extract, and refine. In the recall step, 18 million documents are gathered from the web. The extract step then produces approximately 5 million candidate question-answer pairs. Finally, in the refine step, these pairs are refined to ensure quality, resulting in 10 million high-quality instruction response pairs. The effectiveness of WebInstruct is validated by training models like MAmmoTH2, which significantly outperform base models on various reasoning benchmarks. This approach not only demonstrates strong generalization but also offers a cost-effective solution by avoiding human annotation. Figure 2 compares our dataset curation method with previous studies. Our approach, WebInstruct, mines instruction response pairs directly from the web, avoiding human crowdsourcing. This method yields 10 million high-quality pairs, demonstrating a scalable and diverse alternative to traditional dataset creation. The construction of WebInstruct involves a three-stage data collection pipeline: recall, extraction, and refinement. In the recall stage, the process begins by crawling 100,000 seed data from educational websites to ensure diversity across disciplines. A fast text model is trained using this seed data and 100,000 randomly selected negative documents from Common Crawl. This model is then used to recall 100 billion tokens from an internal Common Crawl. For QE pair extraction, the HTML documents are pre-processed to filter out noise such as ads and boilerplate. Qwen 72b is employed to identify question-answer pairs, with only 30% of the documents yielding naturally existing QE pairs, resulting in approximately 5 million candidate pairs. Figure 3 illustrates the three-step process of constructing WBINSDRUCT. Step 1 involves recalling relevant documents from the Common Crawl. Step 2 focuses on extracting QA pairs from these recalled documents. Finally, Step 3 refines the extracted QA pairs. This pipeline ensures a diverse and high-quality dataset for training models. Figure 4 provides an example from WebInstruct illustrating the extraction and refinement process of QA pairs. Initially, QA pairs are extracted from raw documents, which are then refined using large language models, LLMs, to include detailed explanations. This process results in the final dataset, WebInstruct, which contains 10 million QA pairs. Table 1 provides a comprehensive list of existing supervised fine-tuning SFT, and Continue Training, CT, datasets. SFT datasets, sourced from academic NLP or synthesized by GPT 3.5/4, range from 100K to 1.8 M pairs. In contrast, CT datasets, which are larger but noisier, span from 10B to 120B tokens. WebInstruct, with 10 M pairs and 5B tokens, strikes a balance between scalability and quality, distinguishing itself by its three-step construction pipeline. In the experimental setup, the authors selected several open-source models for fine-tuning, including Mistral 7B, Mistral 8x7B, Llama 3 8B, and E34B. These models were fine-tuned using the WebInstruct method at multiple scales. Key training parameters included a learning rate of 5 × 10⁻⁻6 for Mistral 7B and 1 × 10⁻⁻5 for the other models, a global batch size of 512, and a maximum sequence length of 4096. The training utilized a cosine scheduler with a 3% warm-up period over 2 epochs, employing deep speed with the 0-3 stage on 32A100 GPUs. For evaluation, the authors used a variety of datasets to assess reasoning abilities across different domains, such as GSM-8K, Math, Theorem QA, Big Bench Hard, and ArcC. Additionally, the models were evaluated on code generation tasks and general LLM benchmarks to demonstrate the effectiveness of WBINSDRUCT. Table 2 presents the main results on reasoning datasets, showcasing the performance of various models. Notably, MAmmoTH2-7B demonstrates significant improvements over the base model Mistral 7B, achieving an average boost of 14 points. Similarly, MAmmoTH2-8B enhances the performance of Llama 3-8B base by an average of 8.8 points. The MAmmoTH2 Plus model family achieves state-of-the-art results across multiple benchmarks, particularly excelling in Theorem QA, GPQA, and ArcC, under the 10B parameter constraint. These results highlight the strong generalization capabilities and effectiveness of the models trained with WebInstruct and additional public datasets. The main results show significant improvements in model performance. For instance, MAmmoTH2-7B enhances Mistral 7B's performance by an average of 14 points. Similarly, MAmmoTH2-8B improves Llama 3-8B base by 8.8 points. E34B also sees a 19% increase in math performance after training on WBINSDRUCT. The MAmmoTH2 Plus model family achieves state-of-the-art results across various benchmarks, such as Theorem QA, GPQA, and ArcC. MAmmoTH2-7B Plus's performance on math and GSM is also noteworthy. Additionally, MAmmoTH2-8B Plus outperforms Llama 3 Instruct by 6%, indicating the cost-effectiveness of WBINSDRUCT. The models also demonstrate strong versatility and robustness, excelling in tasks like code generation and general language understanding, further validating the effectiveness of WBINSDRUCT. Figure 5 illustrates how the reasoning performance of the Mistral 7B model improves as the number of instructions increases. The figure also highlights that the SFT loss method is more effective for learning compared to the LM loss method. This improvement is consistent across various tasks, indicating that both model scaling and the use of SFT loss with synthetic data are crucial for enhancing language model performance. Table 3 presents the evaluation results of various models on code generation, instruction following, and MLU Pro tasks. The MAmmoTH2-7B Plus model stands out with the highest average scores of 66.1 on Human Eval Plus and 58.2 on MBPP Plus, outperforming official Instruct counterparts. Additionally, MAmmoTH2-8x7B Plus achieves top scores on Alpaca Eval 2.0 and Arena Hard, and a notable MLU Pro score of 50.4, demonstrating strong general conversational ability and multitask language understanding. In this ablation study, we explore the effects of model scaling and loss functions on language model performance across tasks like Math, Theorem QA, and ArcC. We train models with varying sample sizes from 1M to 10M, using both LM loss and SFT loss. Results indicate that larger models and SFT loss with synthetic data consistently improve accuracy. We also compared two refined models, Mistral 22B x 8 and Qwen 72B, finding that the model trained on merged samples outperformed those trained on individual LLMs, highlighting the benefits of multiple LLMs for data refinement. Additionally, we analyzed the impact of different data domains and sources, showing that education website data consistently outperforms forum data, and that diverse training data is crucial for better generalization across various benchmarks. Table 4 compares the performance of two data refining large language models, LLMs, and their merged samples. The models were trained with the same number of steps and batch size. The results indicate that the model trained on data refined by Mistral 22B x 8 achieves performance comparable to that of Qwen 72B. However, the model trained on the merged samples consistently outperforms those trained on data refined by individual LLMs, demonstrating the effectiveness of using multiple LLMs for dataset refinement. Table 5 illustrates the varied performance across evaluation benchmarks when training on different domains and data sources. Notably, the education website data source consistently outperforms the forum data source, indicating higher quality educational questions. The math domain excels on the math benchmark but does not significantly improve performance on GSM-8K, suggesting that training on a single math dataset may not generalize well to other math benchmarks. Conversely, the other domain, which includes a diverse range of subjects, achieves the highest score on GSM-8K, underscoring the importance of diverse training data. Figure 6 illustrates the quality distribution of 50 sampled refined QA examples. The data reveals that 78% of the examples showed improvement after the refinement process, while only 10% of the examples introduced hallucinations. This indicates that the overall quality of the harvested instruction tuning dataset is generally accurate with a low error rate. In this paper, the authors argue that the web corpus contains a vast amount of high-quality instruction data across various domains. To harness this data, they developed a three-step pipeline involving recall, extraction, and refinement. This pipeline resulted in the creation of WBINSDRUCT, a dataset comprising 10 million diverse, high-quality instruction response pairs, which were used to train language models. The experiments conducted by the authors demonstrated that MAmmoTH2 exhibits significantly enhanced science reasoning abilities compared to baseline models. This work highlights the potential of utilizing the extensive instruction data available in the web corpus to democratize the development of large language models with improved reasoning capabilities. Thank you for watching.